Hi everyone, in this video we will be talking about the kernel shape and the difference between the original Shapley values and what will be the modifications of the kernel shape with respect to uh, these two guys here. So we will also then implement the kernel shape algorithm on pure NumPy. So why do we call it kernel shape? Well, this is actually model agnostic, so which means that we can explain any feature, any model by this model agnostic kernel shape. But in the original shape library, we will see these two guys. These are having the same idea of the kernel shape, but they are faster because shape algorithm is a little bit computationally inefficient. So these guys have some estimations. So instead of estimating the true values of Shapley values, they do some estimations, but they're doing their job good and fast actually. So in the last example, we have the Manchester City, and we say that if in our team if we have Kevin De Bruyne in our subset, this will lead us to 80 points in the leaderboard. But if we don't have this Kevin De Bruyne, if you don't have this guy, so in our subset we have nothing. This will lead to 69 points, right? So in our case, the point, the leaderboard, the thing that give the point on the leaderboard is the machine learning model. But in machine learning model, as you know, we have the fixed size of features. At least most of them we have it. So we cannot directly say that I don't want this feature to be appearing in my inputs. Uh, so we need to somehow simulate the missingness effect. So this is our problem for now. And in our kernel shape, let's say that we have a breast cancer dataset which we have features like mean radius, mean texture, mean perimeter, mean area. And with respect to these features, probably we have 30 features. We have a label that says, let's say that this row, our model predicts 0.1, which means that this is benign. So the cell is benign with respect to these features. So we try to explain whether our cell is benign or malignant. So let's say that we would like to explain this row here. So we would like to explain this row, but we just would like to focus on first four feature. So this is the feature of interest, these guys here. And so this is the instance that we would like to explain why our model says that this is 0.1. So why it is uh, benign actually. Well, so let's dive into some terminology. Let's say that we have a machine learning model that is trained on this dataset, and it is sufficiently good on training and the testing dataset, and it is called F. And if I put some instance, I will have an answer for my prediction. For my cell, I have if it's smaller than 0.5, it's benignant, but then it's malignant. So in order to create subsets, let's say that we have a coalition arrays. For example, one of the coalition array is, let's say that this one, which only consists of 1 and zeros. For all coalition values, you need to go for all the combinations. But let's say that we have this guy for now. And this coalition array, or in our last example, it was a subset actually. So this is one of the subsets, and this is the subset. 0 means that the feature is not present. So this is not present, but for these guys, we have the original features. So, let's say that we also have another function that can take this array and maps it to another array that our machine learning model can take this array and give some prediction. So at the end of the day, we will have f, h, z, and we will have, let's say that 0.15 prediction. So, well, okay, we have the original features with the element of 1. So let's say that, so we say that the instance that we would like to explain is this guy. So I'm using the original features for the ones that includes 1. But for the zeros, I need to do something, right? I need to put some value that, will simulate the missingness and that will act like there's no information carried on this feature. So let's say that we only have 5 instances on our tabular dataset, and for these guys here, I would like to fill these zeros with some instance or with some statistics. So let's say that I would like to take the mean of these 4 guys. Sorry. So with the mean, I have 13, let's say 20, no, it's like 16, let's say, and for this one we have 95 and we have, let's say, that 630. So let's say that this is our mean array, and I would like to fill these zeros with the mean array actually. Why it's like that? Why do we say that? So we would like to simulate the missingness effect. We assume that the mean form of it, represent the most uninformative form of our data. So in order to fill these zeros, we would like to replace it with the most uninformative form of it. So we say that, let's say that these are the mean values. So 16, let me denote it with different color, 16 and 95. And so this is meaningful for our machine learning model to predict. So I can put this array into machine learning model and we can have some predictions. Well, so we can simulate the missingness by that. Okay, but what we need to do for now? Authors proposed an additive feature attribution method, which is called also explanation model, that we will call it G, that takes this, coalition array here and returns a model that we would like to estimate the Shapley values, right? So this guy here returns a model that I will only use the Shapley values for with this form. Why it just takes it? So let's say that this is our feature 1. So so let's say that this is v1, v2, v3, and v4. So this guy here is actually a function that takes these coalition arrays, or it only takes the first one of them. Only one of them, and then returns a model that we can estimate with the linear regression. So with that way, actually, what we are doing is, okay, in my problem, I only have first one and the fourth feature on on my coalition. So if I estimate the effects of it, I will estimate this formula. So this one here is a model that we would like to estimate, and we would like to minimize. Sorry, this is a model that we will estimate its parameters, and these parameters, which are denoted with this, so they are our SHAP values. So this is our Shapley value. So we estimate the Shapley values with that way. But we will need to minimize it, right? So we need to uh, optimize something. So the idea is actually very easy. We have a linear model. We have our payout function, or in the city example, this was the function that gives the point on the leaderboard with respect to the subset. So let's say that we have a loss function that takes our machine learning model, and that takes a linear model. And let me explain it in a minute. And let's say that this function is just doing this. So this is calculating uh, the effect of all the subsets in our dataset, and it takes all the combinations, and it estimates that if I for this subset I have some prediction, and I have a local surrogate model that takes this correlation array and returns a linear model. And then by minimizing this function here, what we have is we have a coefficient of this linear model, and the coefficients are the coefficients of this guy here is actually Shapley values. But as you might remember, we in the Shapley values we have, you know, some kind of weight, some kind of other thing that we shouldn't talk. Sorry, we didn't talk. So we have a weight array right in here. So we have a weight for Shapley values, and the authors have some modified version of this Shapley values, which is called pi x. So we will also have a weight value for each coalition. So this weight function is as follows. Well, which is really similar to the original one, and this is also called kernel. Which explains why we call this algorithm as kernel shape. So in this kernel, we have m as a number of features. So this sum also goes to the, sorry, not in here, but in a linear model, we have m, which denotes the number of features. Again, we have m as a number of features. So in the kernel, we have m minus 1, m choose the number of elements in our subset, multiplied by number of elements in our subset, and the remaining features. So yes, with that way we can estimate the Shapley values by minimizing our loss function. So then, how to solve this problem? I think it can be solved by uh, weighted multiple linear regression could be a good fit. And also we have the weight, so we have the weighted multiple linear regression. And as I know, the matrix solution for the non-weighted multiple linear regression is just for the coefficients we have. Let me change the color. We have our coefficient matrix and x transpose x inverse x transpose y if you don't have any weight. So y is our array that includes, you know, predictions for our instances, and x will be our coalition matrices. So we have four features, and it continues that way. But since we have the weight, the solution changes to this x transpose weight w x inverse x transpose weight and y. And for the shape of weight, we will have a diagonal matrix. Let's say that pi 1, pi 2, blah blah blah, pi 2 over m, and these guys are just 0. So in our solution that gives us Shapley values will be based on this matrix multiplication. Maybe you can think that it can be minimized by, if the dimension is larger, we can estimate it via, gradient descent or something like that. I'm not sure. I think that this is the easiest way to estimate it. So what kind of problems that we can have on the Shapley values or implementation? If we have 20 features, this will be a huge number. Even for 20 features, we will have, crazy amount of combinations. So, which shows that it is RAM killer, computationally inefficient, blah blah blah. And the problem could be the reference array that we are, that our calculations are based on. So in this reference array, we estimated by mean. This is actually problematic. So in some parts, they say that they just sampling, they are just taking random values for each coalition. So they fill the 0 with the random numbers here, and also taking the mean is also another solution. And since we take the mean, as I probably talked on the last video, no, we didn't mention that. So we have phi 0 here. This is our coefficient, right? So phi 0 is called expectation of the model. So I treated it as a, let me call it in a very basic way. So this, I treated phi 0 as a mean array prediction. So what will be the prediction of mean array? What will be the prediction of the array that I fill zeros with it? So the phi 0 is that. So we are comparing our predictions with respect to the mean array, right? But the mean array itself can be problematic. So if we think that we have two-dimensional data set, that we have x and y, and let's say that we have two classes, and we just choose the mean array. And if we just choose the mean array, oops, sorry, the mean will be problematic. the mean will be here, but this will be a data point that is not existed, that has never been existed on our tabular data, or this is just unrealistic. So this could be a problem also. One need to choose it carefully. One need to choose this carefully. Or we just say that I have this prediction here, so I would like to explain this row, but I would like to explain this row with respect to this row. So we just can directly replace these zeros with, instead of 16, we can just the real values of this row, 14, 14 here. This is also an idea. And we will now dive into the implementation, and we will talk the problems of it, in the other video.